Thank you very much, and for the invitation. It's a pleasure to be here. Now I will. It's a post-lunch talk, so it's sort of light. The title reminds us of the basic question: who is us and who is them, right? Because it's not clear whether the others is they, or ourselves. So the starting point is that I can do this here. So this is our garden or our cradle. And then no, I can. And this is a very special place because it is the only known planet that harbors life. Maybe there are others, probably there are others, but it's the only one where we know that life exists. And it's very active climatically, geologically, from almost any point of view. But there are other planets, and I'm talking here about rocky planets, and our neighbors are very different from our planet. I mean, Mars and Venus are sort of rotten planets, so to say, from our point of view, because Mars is very cold. There is water, but it's underground, probably very salty and icy. Maybe there was life. Maybe there was an ocean about more than 2 billion years ago. Venus also, on the other hand, is very warm. I mean, it's 400 degrees Celsius at the surface. Also, it was affected by runaway greenhouse effect. So again, it lost all water. It's a very dry world. I mean, all water was photo-dissociated in the high atmosphere of Venus. And now the atmosphere is basically CO2. Move beyond Mars, we find giant planets, which are gas planets. And Jupiter is particularly interesting for anybody who likes fluid mechanics, planetary fluid dynamics. This is the view of Jupiter we have, typically, this one, something on the right, with the bands, the red spot, and so on and so on. But this is the vision of Jupiter that we got from the Juno probe a few years ago. This is from the pole, from the South Pole, from the North Pole. So a lot of vortices. So it's a very complicated fluid dynamics, much more complicated than we thought. And can be explained by convection, rotating convection, perhaps in part. So it's a very interesting laboratory. But around Jupiter, there are even more interesting objects. One of them is Ganymede or Europa, or other that are around Jupiter, or others that are around Saturn, such as Titan, Encelado, and so on. So these are icy worlds. They are very rich in water, much richer than the Earth. So there is an ocean which can be something between 100 kilometers deep on Europa to maybe 600 on Ganymede. Ganymede is larger than Mercury, so it's the largest satellite, and it also has a magnetic field, which means an intrinsic magnetic field, which means that it has a liquid core and a solid core. But above that, there is ice, real ice, with a thickness that goes from probably 40 kilometers, a few tens of kilometers on Europa, to maybe 100, 150 kilometers on Ganymede. I'm quoting Europa and Ganymede because they're very interesting, because also from the point of view of the search for life, Europa probably has the ocean that is in direct contact with the rock, with the silicates. So there is exchange of matter between rock and water, so all the elements that are needed for water, for life. Ganymede is not clear because it could be in contact. In this case, the ocean should be like almost 900 kilometers deep, or depends upon the equation of state of water, how salty is the water. But it could have a layer of ice 6, which is high pressure, high density ice between the rock and the water. I will come back to Ganymede at the end. If we go to Titan, Titan is even more interesting, so to say, because it is an icy world. It has an ocean. It has a ice crust, but it has a full hydrological cycle of methane and ethane. These are seas and lakes on Titan, and they are made of ethane and methane. They can be connected with each other, and there is rain. I mean, methane is raining. There's a lot of discussion of whether this can harbor life. The rock is in fact clathrates, so this ice with methane nested into the crystal structure. There's a lot of discussion whether this can be a sort. I mean, there could be life there. The problem is that methane and ethane are not polar solvent like water, so there is a lot of discussion about whether they can probably not sustain life. But if we go beyond the solar system, is even you know, there are 2,000, 3,000 planets that have been discovered, and more are being discovered. Particularly interesting are those which are very close to their star, an M-type star, so it's a weak star. And they are very close, but because they are very close, they're tidally locked. Tidally locked means, like the moon with the Earth, means that they always offer the same phase to the star, which means that the fluid dynamics of the atmosphere of such a planet is quite complicated. It's a big convection in the hemisphere, facing the star with a lot of winds, and depending upon whether it is rotating rapidly or not, you can have Coriolis effect or not. And so it is, what I'm telling all these things is that I believe that there is a lot to be done also with, well, there are certainly complex systems, but there is a lot that we can do with simple models in the spirit of complex systems, in the spirit of nonlinear dynamics. So let's look at the simplest climate model. This is for Earth, but it's for any planet with an atmosphere. You have stellar radiation impinging on, then you have surface reflection, which is the albedo, the fraction of energy that is reflected, and then you have the atmospheric composition that is responsible for the greenhouse effect. CO2, methane, water, and other components. And then you have transport, basically meridional transport in the case. I'm thinking about planets that are rotating, I mean normal planets, not tidally locked planets. Normal, again, the others, who is the others? Planets like ours. So you can do this with a one-dimensional energy balance model. You simply have latitude as a variable. You have some sort of diffusive transport from the equator to the poles, and you have to parameterize albedo, the radiation that is reflected, and the greenhouse effect. Some years ago, we started with friends at the Observatory of Trieste, at INAF Trieste, and other people around, to work on this simple energy balance model, which has this form, but in fact, the details are hidden in the names, because T is the diffusion coefficient, and it depends a lot on the characteristic of the circulation. But S is the stellar radiation, A is the albedo, and I is the green. Okay, I can say here. Okay. Everything depends on how we parameterize these terms. I, in the simple old version, like Boudico-Sellers energy balance model, was sigma T to the fourth. But of course, it's more complicated than that. So what we do with our little approach is, which we call ESTM, which is a model for terrestrial-like planets, basically, is that the core is the EBM, but then the radiative convective calculations are done through a column, a radiative convective column from a global climate model with prescribed atmospheric composition, generating a lot of runs, and then a lookup table. And then when you have something, you go there and look at how it's outgoing radiation, and so on. And then the meridional transport is parameterized with, again, general circulation models, and the albedo depends upon whether there is ice, continents, oceans, bare land, vegetation, and something like that. So the first application that I show is by Paolo Simonetti, who is working on that, is Mars. A Mars which is a little with a slightly denser atmosphere than today's. Well, it's 0.18 bar, and then only CO2 atmosphere with CO2 clouds, no ocean like today, eccentricity like today. And so you see as a latitude and the orbital phase, I mean, the period during the year, you can estimate the temperature. And then you see, for example, that for this specific run at the South Pole, which is higher, no? Mars has highlands at the South Pole and lowlands at the North Pole. Then the CO2 atmosphere can condense. So this is not a good outcome. You don't want planets where the atmosphere can condense, of course. And then you can run a lot of different simulations and then see what happens, and then also run the case in which was expected to be there during the Noachian or during other periods of Mars history, with an ocean above the northern part, the northern hemisphere. But what I want to just focus on today here in the remaining, can you tell me when it's like 3 minutes, 4 minutes left? 6 minutes, okay. So I will go faster, but it's looking at the snowball. You know that between about 2.5 billion years ago and 630 million years ago, the Earth went through repeated snowball episodes where the ice almost completely covered the planet. Something like what's now on Ganymede and on Europa, but with continents coming out of the ocean. Well, that's not the case there. Immediately after the last snowball episode, there was the boom of the evolution and the metazoans, like the Ediacaran fauna with the Avalon explosion and then the Cambrian explosion. But how easy is to get this type of solution? Good old ice albedo feedback basically is you have, at some point you have lower temperature, you have increased no ice cover, you have higher albedo, you have lower absorbed radiation, the classic Boudico-Sellers. In reality, it's more complicated than that. You have also variations in the CO2 concentration in the atmosphere, in other position of the continent. So you can do all of these. But right now, let's consider this. So we, at this point, we run about 10 to the 5 cases by varying eccentricity, obliquity, semi-major axis, atmospheric pressure, partial pressure of CO2, and many different initial values of temperature, because you want to have an idea of whether there is bistability. So what you see, you just put everything together, is that the probability, the fraction of solutions going to snowball, of course, increases with the distance from the star, and the fraction of warm solutions decreases. But notice that this happens in a very small region of distance from the star. I mean, the star, for simplicity, is the sun. I mean, has the same luminosity of the sun. So if the luminosity is different, you simply shift this position. But in point 2, with respect to 20% variation of the distance from the sun, from the star, sends you immediately to a snowball, which is well known for Earth. But if you look only at the bistable cases, in the bistable cases, you have 2 different solutions starting from different initial conditions for the same parameters. So you get this. So where do these bistable solutions exist in parameter space? These are the points, and this is the probability of snowball. So here is the eccentricity. Here is the distance, semi-major axis, the distance from, it's the semi-major axis of the ellipse. From it's more than Rayleigh-Bénard because it has a different equation of state and so on, but it's always Pusiness to study, and it's rotating, to study what are the possible exchanges between the heat coming from below, from the interior of Ganymede, to the ice. And then that can be measured above the ice. Thank you very much.
Thank you, Antonello. Some questions? I'm curious, Europa, Ganymede, and even Titan, do you happen to know if there's any tectonic activity on those planets?
On the satellites, yeah. Yeah, Europa seems to have a more active tectonics. Ganymede also, but it has only extensional features. It does not have compressional features. There are plates, but it's doing like that. And it's not obvious why. Now, on Europa, yes, there are. On Ganymede, no. And it could be compatible with the freezing of the water. Could be. But the numbers are so-so. Because it's very strange that there are no compressional features on Ganymede. Yeah, no, there's a lot of work on the surface features. So those cases, but also in the case of a full snowball, you have algae that can stay close to some of the rivers coming from the up mountains, the high mountains, or lakes on top of the ice. And another very interesting point is how the planet did emerge from the snowball. And the classic answer is that volcanoes were continuing to emit CO2, and there was no weathering of the silicates, so it was just accumulation of CO2 until the whole thing exploded. I mean, but at the same time, it seems to be not the also it's very young, polar clouds. So the coming out of a snowball is the active area of research that requires addressing. Interesting is that immediately after the disappearance of the snowball, climate down to very warm conditions, and then help this booming evolution of life.
Thank you again, Antonello.